Welcome to Krishna's classroom. I'm continuing the seminar or the webinar that we had yesterday on the real line R. Let us briefly recall what all things we did yesterday. We first introduced what are called the Pianos Axioms. And that defined the set of natural numbers. That was the beginning. And the 5 axioms that we wrote determines a set which we choose to call the set of natural numbers. Then we introduced addition, order and multiplication. So we defined what addition is, what you mean by the order, and in the addition itself, from addition we came to order. And then of course we introduced multiplication. We explored the properties of that. In fact, we didn't prove much on this, but many of the familiar properties can be derived from these Pianos axioms and the operations that we have introduced. There's a string of results that follow from there. I think we listed them out. In the nutshell, what is that we have observed? We observe the following structure. I mean, this is something very typical of this. So this is, we are working on N. Yeah. So the first property, that observation that we make is the following. Every natural number X has a unique natural number lying next to it. Given by so what is important is that there is a concept of nextness here to the right. What is the analogous thing to the left? Every natural number X not equal to 1 has a unique natural number to its that means if Y denotes this number, then Y prime equals to the given X. That is a relation that we have. So that tells you the nextness concept in that. That is, there exists a concept of nextness in. So this is something very interesting. Because you see that, what do you mean by nextness? If you have two elements in the set having the property that in between there is no other element, then you say the one lies next to the other. Okay, so this property is a salient feature of the set of natural numbers. Okay, this gives also what is called the discrete structure. Okay, so the set of natural numbers form a discrete set. Now this gives discrete structure. Now the third property is that if M is a subset of N, then there exists a smallest element in it. No matter which subset you choose in N, there is always a smallest element in it. Now the fourth property that we look at, we observe is that N has no largest element. That means if there is an x, then there is an x prime or x plus 1. Then fifth property is this. This is important. The equations are given A comma B belong to N. The equations A plus X equal to B and Ax equal to B may or may not have a solution. In fact, you see that the order structure is derived from the first one. So this leads to order structure. And this, later on you will see that this leads to rational numbers. These are the things that you observe. Okay, before I go any further, let me also make some remarks about the induction axiom. So, what was the induction axiom? The induction axiom said the following. That is the fifth one that you had. Fifth axiom. It said if E is a subset of N such that 1 belongs to N, 2 n belongs to implies n plus 1, which is equal to n prime belongs to then this 1 belongs to m. I mean, m is contained in n such that 1 belongs to m, and n belongs to m implies n plus 1, that is n prime belongs to m, then m is equal to. Now, this is the all important induction axiom which we use so frequently using the method of induction. Probably this is not very clearly emphasized when you invoke the induction axiom. You don't even realize that you are doing it. Okay? For example, suppose you look at this problem. I mean, I am just taking a simple problem. The problem is this. See, what is the sum of the first n numbers? What is this? This is actually, how do you do it? You put n plus 1 plus etc. So you get to s is equal to n into n plus 1, and therefore s is equal to n by 2 into n plus 1. But how do you prove that this is actually this? Let's explore that. Just to have an understanding of this, the power of this axiom. Without that, you can't do anything. So I just take this out. What does this axiom say? This axiom says that, as I have written here, if 1 belongs to m. So how do we write the first line, which is not often written? So let by 2. This formula is valid. Okay. Now we want to say that this is true for every n. First of all, is it true for some n, or is m empty? This is first we have to look at. So check whether it is true there is at least some number in this class. And you easily verify that when n is equal to 1, you see that s is equal to, if you apply the formula, it is 1 plus 1 into 2 by 2, which is equal to 1, which is true. Which implies 1 belongs to okay. So M is non-empty and 1 belongs to. Now suppose K belongs to M. What is the meaning of that? The class of numbers M is the one for which this formula is valid. So K belongs to M. If K belongs to M, what you have? The corresponding S is going to be K into K plus 1 divided by 2. This is what you have 1 plus. Okay. So the sum up to K numbers. Let me write that. This is just to tag this formula. Now, if you want to apply this, then what does it say? If n belongs to M, implies n plus 1 belongs to M. So we have to say that K plus 1 also has this property. So what is Sk plus 1? This is equal to 1 plus 2 plus K plus K plus 1. And this, you know, you have the assumption that is this is equal to Sk plus K plus 1, which is equal to K into K plus 1 by 2 plus K plus 1. And what does that give you? That gives K by 2, which by definition of Sk it is equal to therefore it follows that this implies K plus 1. So your script M has the property that 1 belongs to it, and if K belongs to it, then K plus 1 also belongs to it. Therefore, by the induction axiom, which defines the natural numbers, M has to be the whole of. Therefore, this is the logical part of it. But what one normally does is that 1 belongs. You just check whether 1 belongs to it, K belongs to it, then K plus 1 also belongs to it. Then you immediately write down it is valid for all. But no one realizes that it is based on the strength of one of the fundamental properties, or one of the basic axioms of the number system. Okay? So that's just a remark which I think is of importance to the students. So we have seen that this is all about the natural numbers, and we have built a wonderful system with a nice structure having 3 structures superimposed on it, one coming from addition, the other one coming from order relation, the other one coming from multiplication. What if we go from there? Then we went on to build what are called fractions. Fractions were identified as I was pointing out yesterday, 1, 2, etc. Then 1, 2, etc. Just you take a graph paper and do this. That's very interesting. In fact, it's nice to work this out. Okay. This is what you call soiling the head to understand mathematics. Okay. So we identified Mn, where n belongs to n also belongs to n. So this as a fraction. So a fraction was defined like this, which we traditionally write as n by m on the top and n below. I mean, that order is very important in which you write, and its implication is also very important. Therefore, you see that if you look at the class of all Mn, this is n cross n. The elements of n cross n are Mn. These are the set of points. Okay? And you know the definition of n cross n. I don't want to go to that. So these are essentially these lattice points that you have. Each one has both the coordinates as natural numbers. Now that's the point. Now what we proved, or when then we introduced what is called addition. Order and what is called multiplication. Then we came across a problem, a weird problem. The problem was this. You see, we know that you have a cake and subdivide this into 6 equal parts. Then if you take 2 such pieces, it constitutes what is called 1/3 of the whole. Okay? If you divide this into 3 parts and then take 1 piece, that is also 1/3. If you divide this into, say, 3n pieces and take n parts from it, equal parts from it, that's also 1/3. So they are all 1/3. So in fact, you see that there are so many fractions which represent the same thing in our perception. How do you put them all together? This was a point.